In last video, I showed you how to install Olex2 from scratch and some basic settings. Now, I want to show you how to use Olex2 to solve and refine your first crystal structure. If you haven't installed Olex2 yet, please watch my previous video for the installation guide. I will put a link down below for you. Before we start the program, make sure you have a dataset to play with. If you don't have one, please click the link below to download the sample dataset before proceeding. The best way to learn a program is to practice on a project. I will use my dataset throughout this demo. I encourage you to do so too, simply because you can follow me better with the exact same dataset. You can practice with your own dataset after you get a hang of it. Go ahead to download and open the data folder. Normally, you will need to copy and list 2 files off the instrument computer if you run the instrument yourself. Or you can get the files from the crystallographer who ran your samples. One is an instruction file. The other is a HKL file. Their file extensions are INS and HKL respectively. A lot of times, the INS file can also be replaced by RES file. And it is probably more common to have all 3 files together: INS, RES, and HKL. Anyway, let's open the INS file first with Notepad. Then I will briefly explain the contents of this file. So this instruction file is for the Olex program to follow. The first line is a title card. It is a file name of your dataset. Notice Olex program recognizes these 3 to 4 letter cards as input command. You can get the detailed information about these cards on this website. Notice this is actually the same website where you get the Olex program package. If you have watched my previous video about how to install Olex2 or Olex Learn, you would know what I'm talking about. Anyway, I suggest you add this website to your favorites so you can access it anywhere in future conveniently. Back to the INS file. The REM is short for remarks. Any lines started with this card are ignored by the program. The second line, if you ignore the REM lines, is a cell card. It is the cell parameters and other information. Here it is the wavelength used for the data acquisition, 0.71 nanometer. If it is copper, it will be 1.54 nanometers. These numbers are the cell metrics A, B, C, alpha, beta, gamma. This Z error card, Z indicates how many formula moieties you have in the unit cell. In this case, it is 4. And these numbers are the error values for the above line, the unit cell parameters. Of course, the smaller the better. Lant is short for lattice. This indicates the lattice type. Negative sign here indicates it is non-centrosymmetric. 1 indicates it is primitive cell. These 3 lines started with same show the symmetry associated with this space group. For each specific space group out of 230, there is a specific set of symmetries associated. Then the SFAC card. This line indicates the element types involved in this structure. Here they are carbon, hydrogen, oxygen, sulfur. Unit card tells how many of each element types are in this unit cell. We can skip these cards for now. If you are interested, you can always go to the Olex program website for the details. Finally, I want to talk about the HKLF4. This is a HKL data format. It usually takes the value of either 4 or 5. 4 is for single crystal, and 5 is for twinned data. The ins file always ends with this end card. Now let's open the res file. The res file is a result file after you solve the structure. You will see it is very similar to the ins file. The major difference, or the new contents, are the atoms here, and the res file is the results of the solution. It is also the starting file for refinement process. Now let's open the HKL file. You can see it is of this specific format. There are 5 columns. Each column is HKL F observed square, sigma of F observed square. HKL are the Miller index, and F observed square is the diffraction intensity. These intensity values are experimentally observed values and will be plugged into this type of equation. Of course, this format is dictated by the HKLF card in the ins file. And this HKL file always ends with the 0 lines. The remaining lines are not needed by the program, but helpful for you. Since I'm going to show you how to use Olex2 from the very beginning, I will delete the res file and start with the ins file here. In future, you can always start from the res file directly if you have one, and proceed directly to the refinement stage. Again, here I'm doing this solely because I want to show you how to solve the structure from scratch. Now let's get on to the Olex2 program. You can start the program first, then browse to your data, select and open it. Or you can use your Windows File Explorer to navigate to the data folder, then right-click, choose Open with Olex2 to open it. Another way, you can designate Olex2 as the default program to open this ins and res file. Then in future, you only need to double-click on it to open. Anyway, since we haven't solved the structure yet, so the window is empty. And you can even click this folder icon within the Olex2 interface to visit your data folder. We still don't have a res file here yet. You will notice there is a new folder generated by the Olex2 program. To solve the structure, it is actually very simple. Click Work to expand this menu. Click the arrow by the Solve button to expand the menu. Then here, click the down arrow. You should have multiple options available. If not, please refer to my previous video of how to install Olex2 from scratch correctly. Then you will get these options. You want to choose Olex T most of the time. Then click Solve. Aha! Within a matter of seconds, you get your structure. Press and hold your right mouse button and move up to zoom out. Press and hold left mouse button to orbit the view. Normally, you don't need to pan your structure, but if you do, press and hold both left and right mouse button and then move. It will move the structure in this plane. If you need to center the structure again, just type center down in the command line, then press Enter. Now it is a good time to introduce the interface of this program. The top menu is a file menu bar. This is less often to be used other than open, close, and save the files. There are other functions, but we can always access them from elsewhere. The middle section is the workspace. Your model is here. To the bottom is the command line. A lot of the Olex2 functions, if not all, can be realized by typing commands here. To the right is the function, property, and information window. We will spend more time here later. This is your initial model for your structure. At this point, it could be wrong, it could be right. You need to refine the structure to find out. Also, it really helps if you have an expected structure from the sample owner, as whoever made the sample knows the best about the sample. They probably already know what structure to expect, so definitely consult with them. If you have no initial information from the sample owner whatsoever, then you need to have very good data. Otherwise, your model is very likely to be incorrect. You need to know at the minimum the element types in the sample, which can be learned from element analysis or EDS analysis. Now, if you click the folder icon, you will notice you have the new res file now, which is generated by clicking the Solve button just now. Next step, click the arrow by the Refine button, select Shellax L, and put 4 in the cycles, and put 10 in the peaks. This is telling the program to include 10 cubics in the plot. Then click Refine. There are always multiple ways to do the same thing in Olex2. For example, you can use keyboard shortcut Ctrl+R to refine, or you can type in the command line refine, then press Enter to refine, or you can type in refine 4, 10, press Enter to refine. All this will tell the program to refine. I personally prefer keyboard shortcuts. You can do whatever you like. Refine a couple of times until the shift value stabilizes. It may not approach 0 at this point. In this case it does, but it may not in other cases. Don't worry. In the end of this tutorial, it will get to 0. At this point, you just want it to stabilize. One neat thing about the Olex2 program is that the interface is very user-friendly. They color-code these refinement indicators. Green is good, orange, red are not good. So if you refine a couple of times, the shift will fall within spec and turns green. Next step, assign the atom type correctly. As I mentioned earlier, this initial model could be wrong, so you need to consult the sample owner to get their expected structural models. In this case, I know it is correct. However, for the purpose of the demo, let me mess up the model first. I will show you how to modify it later. Let me make this carbon to nitrogen first. and refine a couple of times until the shift stabilizes. Here is actually a good time to bring up an interesting note. You know, these isentropic balls represent atoms, and their size should be similar. If one atom is significantly larger than others, that could mean one of the two things. One, it could be disorders, which is a more complicated subject which I will cover in my future videos. Or second, it could mean the atom types are assigned incorrectly. The real atom type should be lighter than what it is now, which is the case in this situation. It should be a carbon instead of a nitrogen. Conversely, if you have an atom significantly smaller than others, that means it should be heavier atom than now. For example, let me make this sulfur to be carbon. Then refine. Now you see it becomes awfully small, and all of a sudden, so many red areas showed up. Now let me show you how to assign the atom type. Again, I will show you two ways. One way is through this window. Suppose we want to assign this atom to be sulfur. Then click on this atom to select. It turns green when it is selected. Then you click sulfur. Let me undo it to show you another way. Click sulfur button first. Notice the cursor becomes a special pointer with sulfur labeled on the tip. And this orange message window to the bottom right indicates you are in a naming mode. Then you click on the atom you want to assign to sulfur. When you are done, press Escape on the keyboard to exit the naming mode. The second way, which is my preferred way, is to click to select the atom first. Then in the command line, type name C for carbon, press enter. It will take effect. Now refine a couple of times until the shift stabilize. Good enough. When you think you get a correct model by assigning the atom types correctly, then move to the next step. Convert the isentropic model to anisotropic. Basically, if you open the res file now in Notepad, you will notice for each atom, it has atom name, atom type, X, Y, Z coordinates, occupancy. Final column is temperature factor, B or U. Since it is an isentropic model at this point, so it only have one value for the temperature factor. We will revisit this file after we convert to anisotropic models. To convert to anisotropic models, simply click this ellipsoid icon. It will change to anisotropic model and refine, because this box is checked. Alternatively, you can type anis and press enter. That will also convert it to the anisotropic model. Refine a couple of times until the shift is stabilized. Now let's revisit the res file. Here I will show you another way to access the res file quickly, as this tutorial is to expose you to various functions of Olex2. You type edit res, press enter. It will open the notepad. Now you will notice there are 6 tensors for the temperature factor. Okay, close the res file. You can type edit to access other file types this way, such as ins file, zip file. For example, if you type edit zip, it will open the zip file. Here you can modify the zip file to prepare for publication. I will cover this topic in my future videos. Be sure to subscribe to follow if you are interested. Next, to add proton to the structure. Again, there are multiple ways to add proton. I will show only 2 ways here. You can click add hydrogen button here, and this box is checked. It will add hydrogen and refine. Or you can type and to add hydrogen in the command line. Let me delete the hydrogen first by typing $H to delete the hydrogen. Then I type H and press enter. It will do the same thing as you click here. This H and command in the command line is more powerful and versatile when the button click fails. For example, sometimes the program fails to assign the hydrogen correctly. Then you can use the command with some modifier to force it to add hydrogen in your desired way. To give you an example, suppose Olex2 fails to add hydrogen to this atom. Let me delete this hydrogen first. What I will do is select, then press delete key in the keyboard. Suppose Olex2 did not add hydrogen to this carbon by the automatic method here. Then what you need to do is click on this carbon to select. Then in the command line, type in H and. As you know, this is aromatic carbon, so you type 4,3. Then it will add the hydrogen correctly. And suppose this is actually a secondary carbon, and the program added only 1 proton there, but you want to add 2. So you select and type in H and 2,3. This way, it will force the program to treat the carbon as secondary. Press enter. Now it will add 2 protons. Of course, in this case, it is indeed an aromatic structure, and the program did a very good job by itself. So we're going to delete this proton and let program do its job by itself. Then refine a couple of times until everything is stable. Good enough. Next, check the box by weight to let the program update the weight value iteratively. Refine a couple of times until the shift is stable. Next, check to see any parameters are out of spec. So just check if you have any orange or red highlights. In this case, there is an orange update icon here, and it says here the cell contents from unit instruction and atom list do not agree. So you simply click this icon to let it update the list, then refine, then that error is gone. And now you notice there's another error, flag number of 0.95. It says here, absolute structure probably wrong, invert and repeat refinement. So flanker parameter is a more complicated subject. I will discuss it in future videos if I have time. But briefly, this parameter usually is in the range of 0 to 1. 0 means your absolute structure is correct. and if it's close to 1, that means it is just the reverse. That means you need to invert your absolute structure hardness. If it falls in between, i.e. it is 0.5, that means you are missing an inversion center. Anyway, to invert the current hardness, you just type in the command line inversion -F, then press enter. Then you press Ctrl R to refine, and you will see now the parameter fall within spec and turns green. And continue to click refine a couple of more times until this weight value turns green. Okay, congratulations! You have successfully solved and refined your first crystal structure. I'm very proud of you as you have come so far. Obviously, this is a very straightforward dataset, so there is no challenges here. In real life, you will run into all kinds of problems. But don't panic. About 50% of the times, the structures are like this, so you can process them by yourself now. For more challenging ones, I will try to make a series of demos to teach you how to deal with them. In future videos, I will cover how to prepare for publications, including how to add necessary information to the SIF files, such as instrument information, crystal morphology information, author information, etc. How to combine multiple SIFs into one SIF and give each individual structure a unique running number, such as structure 1, structure 2, how to run CheckSIF to examine your structure by the online CheckSIF tool, how to add author response to SIFs if CheckSIF finds some alerts, how to use Platon to add missed symmetries, how to deal with disorders, how to process tuned data, tips for using Olex2, etc. Before my next video is out, now you can delete all the files in the data folder except the ins and HKL, and you start from scratch to repeat the process. After you get a good feeling about it, you can move on to your own dataset if you have. Thank you for watching and see you next time. Please don't forget to subscribe to follow future videos if you are interested. Bye.